In this chapter, firstly we speak about the properties of solids. As we all know that one of the three basic states of matter, solids have strong intermolecular force of attraction and it has specific shape, mass and size. Secondly, we study the difference between crystalline and amorphous solids. Crystalline solids have definite ordered arrangement of constituent particles. These constituent particles can be atoms, ions or molecules. But an amorphous solid does not have ordered arrangement of constituent particles. Also, crystalline solids have sharp melting point, whereas amorphous does not have sharp melting point. A unique property of crystalline solids is they are anisotropic. Surely you will have a doubt on anisotropy then. What is anisotropy? Anisotropy means that few physical properties of these solids such as conductivity, refractive index, etc. they have different values when measured in different directions. We can expect the opposite behavior from amorphous solids, that is, they are isotropic in nature. Also, crystalline solids have definite values for enthalpy of fusion and they are known as true solids. Similarly, we can say that amorphous solids doesn't have definite value for enthalpy of fusion and they are known as pseudo-solids or supercooled liquids. Amorphous solids exhibit tendency to flow, not as fast as liquids but very slowly, so they are termed as pseudo-solids where pseudo means false. Then moving on to the classification of crystalline solids. Based on the binding force between the constituents and the nature of the constituents, they are classified as ionic solids, covalent solids, metallic solids and molecular solids. Ionic solids. In this type of solid, the constituent particles are ions, which mean the solid is composed of anions and cations. They are held together by electrostatic force of attraction forming ionic bonds. That is why they are hard, brittle and possess high melting and boiling points. They conduct electricity in molten state but not in solid state. Examples for ionic solids are sodium chloride, cesium chloride and magnesium oxide. Covalent solids. They are also termed as atomic solids or network solids. Constant particles are held together by covalent bond. Covalent bonds are strong, therefore the atoms are held very strongly in the solids. Also, they have very high melting point. They do not conduct electricity due to the absence of ions and free electrons, but graphite is an exception in this case. Few examples for covalent solids are silicon carbide, quartz and diamond. The third one is metallic solids. A positively charged central metal atom is surrounded by free moving electrons in metallic solids. They are held together by metallic bond. They are well known for their electrical conductivity due to the presence of free mobile electrons. Their melting points vary from material to material. Important properties of metallic solids are malleability and ductility. Malleability and ductility are two well-known terms you studied in your lower classes. Examples for metallic solids are sodium, zinc, bronze, etc. The last one is molecular solids. Usually molecular solids are soft. They may exist in liquid or gaseous state at normal temperature and pressure. They do not conduct electricity. They are again classified into three categories based on the nature of binding forces. They are polar molecular solids, non-polar molecular solids and hydrogen bonded molecular solids. Few examples for molecular solids are solid HCl, solid hydrogen, ice and solid iodine. Hereafter, we give importance to crystal and related topics. We will study in detail about crystals. We define lattice point as the point which indicate relative positions of constituent particles in a crystal. As we told already, the constituent particles can be atoms, molecules or ions. Then what is crystal lattice? Crystal lattice is a three-dimensional arrangement of points showing the ordered arrangement of constituent particles in space. You must imagine a three-dimensional image of a crystal to understand this concept. A unit cell is the smallest repeating unit of crystal lattice. It has the shape of crystal. A unit cell is defined by three edges which are represented usually as A, B and C, and the angles between the edges alpha, beta and gamma. Alpha is the angle between the edges B and C. Beta is the angle between the edges A and C. And gamma is the angle between the edges A and B. Unit cells are classified as primitive and centered unit cells. In primitive unit cells, the constituent particles occupy only the corners of the cell. Centered unit cells are again divided into three categories. They are body-centered, face-centered and end-centered. Body-centered unit cells have one constituent particle at the center of the body as well as at the corners. In face-centered unit cells, the constituent particles occupy the corners and also at each faces of the unit cell. In case of end-centered unit cell, each constituent particles are present at the two opposite faces along with the particles at the corners. There are 7 types of unit cells or crystal systems. These crystal systems differ from each other on the basis of the values of A, B, C and alpha, beta, gamma. The 7 types in the table. Please note down the different types of crystal systems and their possible variations. The relationships of the parameters A, B, C, alpha, beta and gamma are also given accordingly. Most suitable examples are also listed. You may please note that cubic system is most symmetric and triclinic is the most unsymmetric system. Here in the table we can see that there are total 7 crystal systems and each crystal system has different types of space lattices, making a total of 14 space lattices. They are known as Bravais lattices, named after the French mathematician. From these space lattices, we can find the number of atoms in a unit cell. Consider the constituent particles as spheres. We can make out that each corner constituent is shared by 8 unit cells, making the effective number of constituent per unit cell at the corner 1 by 8. So, a primitive cubic cell has 8 corners and each corner has 1 by 8 of constituent. Therefore, the number of atoms per unit cell of a primitive cubic cell is 1. Solid fluorine is an example for primitive cubic cell. While coming to end-centered unit cell, one constituent particle is present at the center of any two opposite faces. Similarly, FCC face-centered cubic cell has the effective number 1 by 2. 6 faces will have 1 by 2 of the constituent, making it a total of 3 particles. Adding 1, which is due to the corners, makes it 4 constituent particles in FCC. Crystals of sodium chloride, copper, calcium, aluminium, etc. are examples for FCC. Body-centered cubic cell has one constituent at the center and 1 by 8 portion at each corner. So the total number of constituent particles will be 2. Cesium chloride crystal, sodium and potassium are examples of this type. Remember one thing, the coordination number of a particle in a crystal is defined as the number of particles immediately adjacent to each constituent particle in a crystal lattice. We have some calculations in this unit based on packing efficiency, which is nothing but the percentage of total space occupied by the particles. A simple cubic cell has a packing efficiency of 52.4%, HCP and CCP has 74% and BCC has 68%. Let's speak about close packing in 3-dimensional solid structures, which will tell you the different types of arrangement of constituent particles. In 1-dimensional close packing, the spheres are arranged in a row so that each sphere will be in contact with 2 spheres, hence the coordination number is 2. 2-dimensional close packing can be either square close packing or hexagonal close packing. If the first row of spheres is represented as A, the second one will be again A, so that we get A type of arrangement. Hence the coordination number is 4. In the case of hexagonal close packing, the second row is placed in the depression created by the first row. This trend continues in 4th, 6th and 8th layers and so on. This will give rise to AB-AB type of arrangement. Also, the coordination number will be 6. The most important one is close packing in 3 dimensions. Here you have to imagine the spheres arranged in 3 dimensions having 3 axes. Here 2-dimensional layers are placed one over the other. If a 2-dimensional square packing layer is placed on another 2-dimensional square packing, we get AAA type pattern. Consider a 2-dimensional hexagonal close pack layer A and a similar layer is placed over it in such a way that the second layer is on the depressions created by the first layer. So a tetrahedral void is formed. The other triangular voids of the first layers are covered by the triangular voids of the second layer, and the resultant voids formed are octahedral voids. In another case, if the third layer of spheres is arranged by covering the tetrahedral voids of second layer, AB-AB type of arrangement is expected. This is called as hexagonal close packing and is found in metals such as zinc and magnesium. If the third layer of spheres are arranged to cover the octahedral voids of the second layer, ABC-ABC type of arrangement is observed. This type of close packing is FCC or cubic close packing and is found in metals such as silver, iron, nickel, gold, copper and aluminium. Stay tuned for the second part of the solid state.